Hi there, welcome. Thank you so much for staying around, and we're ready to start now. And welcome to the first Kepler lecture of this semester. The Kepler lecture series is a part of the Center for Planetary Habitability, FAB, which is here at the University of Oslo. And today we're glad to welcome Eric Gaidos, who's a professor at the University of Hawaii. And he's coming to us to talk about lava worlds. And Eric he studies the formation and evolution of exoplanets, and he has he's trained originally in astronomy from the Massachusetts Institute of Technology, and they did a postdoc. This is all in the 90s at Caltech. And after that, he went to the Department of Earth Sciences at the University of Hawaii, which is where I know him from, because I was a professor there at the same time, and I overlapped with him. And in fact, he's currently residing in my office, my old office at the department there. So he has a background in astronomy and experience with Earth science problems, and so that kind of makes him an ideal Kepler lecturer for studying the habitability of exoplanets. And today he's going to be talking about a certain kind of exoplanet. He's going to introduce it, but it's lava worlds. So thank you, and we're looking forward to your talk.
Thank you. And I have 15 minutes, right? So thanks everybody for hanging around. I will try to speed things up so that you can get back out in the rain as you wish. I want to do just a quick poll here. How many people last Sunday tried to see the total eclipse of the moon? Wow, excellent. Right. I said try. I did try, and I wasn't very successful. So just to Yeah, I know, but it's cut off. So the picture you're seeing actually is not from last Sunday, but it just gives you an idea of what you would have seen had the clouds cooperated or gone away. And if you were probably more eastward of here, where you would be able to see the moon rising by the time that totality happened. So I'm sorry about that, but actually that gives me an opportunity to do a little promotion for where I'm from. I'm at the University of Hawaii, and so I am a resident of this island here, Oahu. Hawaii is an archipelago, so it has several islands. The volcanoes you may hear about, the active ones, are on the Big Island, which is on the right of the screen. I am here where the main campus of the university is, and also the Institute for Astronomy. And just in case in March you need any more incentive to see the total eclipse of a moon, the next one there will be March 3rd. Okay? If you want to wait here, you have to wait until December 31st, 2028. Okay? So, but you are all welcome to come. Hawaii is a nice place to be that time of year. We do have volcanoes. I know there are other places of volcanoes. Ours are bigger, so and they are extremely active. We also have one of the world's premier observatories, Mauna Kea, which you might make out in this picture at the summit. This is a view from the International Space Station looking down, and at the top of that very high mountain, over 4,000 meters, is a cluster of telescopes, some of which I use to do observations that I will briefly mention a little bit today in the context of the topic. So I want to segue to exoplanets and what I work on by actually going back to this picture, what you see, and asking the question, why isn't the moon completely dark? The Earth is basically blocking all the light from the sun. And so the Earth is, since the moon is about the same size as the sun as seen from Earth, and the Earth is much bigger, the Earth should block out all of the sun, but it doesn't, right? And of course, most of you probably know that this is due to scattering and refraction of sunlight through the Earth's atmosphere around the Earth, the solid Earth, incident upon the moon. And if you were to go to the moon and look back, you would see a total eclipse of the sun, but the light wouldn't completely disappear because you would see this ring, which is essentially a sunset everywhere on Earth, where light is passing through Earth's atmosphere and being refracted and scattered and seen as a tiny red thin crescent all the way around, and that's what provides the illumination that you see. So the geometry here is essentially this. You're on the Earth and you're looking at the moon, and the moon is acting like a giant reflecting mirror, a very bad mirror, but a very big mirror, which is seeing sunlight passing through the Earth's atmosphere, and just like a sunset that you would see on yesterday, the Rayleigh scattering of the atmosphere of the Earth is scattering away the blue light, letting the red light pass through, hit the moon, scatter off the moon, which is a gray reflector, and then reach your eyes. So I bring this up because actually this is one of the exact same techniques we use to study very distant worlds around other stars, or exoplanets. And the revolution in exoplanet research is that these measurements, which were previously unimaginable, not even thought possible, are able to tell us in some detail about the nature of those worlds orbiting around other stars. So here we are seeing from a great distance a planet passing in front of the star, sort of by chance geometry, and some of the starlight passes through the atmosphere of that planet, if indeed it actually has an atmosphere. And what we do in Hawaii and Mauna Kea is actually study that effect to tell us something about those atmospheres. This is possible, of course, because we know of planets, actually we know of thousands of these planets, that are fortuitously aligned, or their orbits are aligned such that their bulk passes and blocks out a very small fraction, usually less than 1%, of the light from the star. And this technique allows us to actually detect the planets from the first place, because this appears as a dip in the light from the star if you monitor it versus time. So the planet's orbital motion carries it across the face of the disk of the star, and that occults a small fraction of the light, and we see that change, that slight dimming of the starlight, with a sensitive enough instrument. We can do this a little bit from the ground, but the true revolution has been from space, where we were able to actually see and detect thousands of these objects thanks to telescopes that have been launched into space. And so the histogram that I'm showing there is a cumulative count of all the exoplanet discoveries in the last basically 30 years, 3 decades, since I got a PhD. And the bulk of those discoveries are the purple ones, which are through the transit technique. And so every one of those objects is potentially an object of study to understand its atmospheres and then perhaps something about its composition. So these are the result of many such of these missions. I've just shown pictures of the kind of rogues gallery of the primary ones, starting with the ESA Kines mission Kourou, which was launched at the very beginning of the 21st century, and then later Kepler, and now TESS, which is still flying and going, and then CHEOPS, which is a joint ESA-Swiss mission. And just stay tuned, because for those nations which are part of ESA, and Norway is one of those, at the end of next year, there will be the launch of a mission called Plateau, which will carry this even further and produce thousands of more of these discoveries. So this transit method, what we call it, where the planet blocks some of the starlight, is sensitive to how big the planet relative to the star. And if you know how big the star is, that's another story. Then you can figure out how big the planet is, what its radius is. And you also can monitor these transits occurring at regular intervals, right? Because it's a Keplerian regular orbit. So you get the orbital period and you get the radius, and we can easily now produce plots like this, which show thousands of planets in radius versus orbital period. And of course, orbital period, thanks to the original Kepler and Tycho Brahe, is related to how far the planet is from the star. So here you can see that this distribution actually breaks up into clusters, which I've given the names that we astronomers have sort of informally called them, even without knowing very much about the objects themselves. Notice that the y-axis, the vertical axis, is planet radius in Earth units on a log scale, and so Earth was down basically at one of these purple points towards the bottom of this diagram. So there are a lot of planets about the size of the Earth, some smaller and a little bit bigger, and they're also mostly closer to the star than the Earth is. That's a bias on our part with the detection method that we use. Closer to the star, of course, means warmer, and some of these planets are a lot warmer, and this leads me then to tell the story a little bit of lava worlds. So much of what I will talk about today is based on a review article that some co-authors and I wrote during the pandemic, actually, and published in 2021. And so there's the reference below for those of you who want to go into a deep dive into lava worlds. You are welcome to download this. I think it's freely available. I think what's special about this review article, for me at least, is that all of these co-authors on there, I'm the senior author, are actually graduate students. They were graduate students in my science writing class, which I teach from time to time at the university. And our joint project was to write this review article. And it was mostly done by the time the class ended, and then it was published a bit later. But all these people contributed in different ways with different expertise and different interests to this work. So, to begin with, to make sure we're all on the same page, I should say, what is lava? Okay, because I say lava worlds, and for the non-geologists, lava is just magma that has erupted to the surface of the planet or the Earth. Well, that's fine, which leads then to the question of what is magma. So magma is just basically molten rock, silicate melt, but for geologists, magma includes up to 3 phases of the material. So, of course, the liquid phase, the silicate melt, but also it can be very rich in the crystalline or solid phases, what we call partial melt, and also gases are dissolved in there. So the analogy is what we used to call in my time in the US a Slurpee, which is an iced drink with carbonated water and usually flavored with a lot of sugar. So a lava world, we loosely define, is a planet where there is an ocean of this magma that is either at the surface or near the surface, okay? And another term for that is basically a magma ocean planet. So imagine Earth, twin gone bad, where our beautiful liquid water oceans are replaced by molten rock. So Earth is not a magma ocean, where we don't have the energy sources to sustain temperatures where rock melts. So in the Earth's interior, rock will melt at start melting at a specific temperature, which we call the liquidus, or the solidus, excuse me. And then at some point, the rock is completely melted, and at that point, we call it the liquidus. So there's some boundary between totally solid and totally liquid, or melt, which is the purple zone in this diagram. So this is the frontier. And like most phase diagrams of matter, the 2 fundamental parameters are the temperature, obviously, but also the pressure, because the pressure tends to favor the denser phase, which is usually the solid. And so you have a pressure-temperature diagram. On one side, there's basically the solid phases, and then the other one is the melt itself. And in the Earth, as you would travel down through the interior of the Earth, you would follow a trajectory called the geotherm, which is basically represented by this dotted green line there, and you can see that it's basically completely in the solid phase. So obviously, that's not true everywhere on the Earth. There are places where that green line crosses into that zone of the melting, and Hawaii is one, Iceland is another. But overall, the bulk Earth, the bulk silicate Earth, the upper part, is solid. Okay, so that's why we are not, at least at present, a magma ocean planet. But our planet, and probably every rocky planet in the solar system, and perhaps without exception around other stars, was once a lava world in some sense, because planets formed by a very, very energetic process of accreting from smaller bodies, and the gravitational energy which was released would go into the heat and melt some, or actually perhaps most, of the parts of the planet. And so we were, and many planets originally were, a lava world. And in ways that I don't have time to go into details here, those conditions of having that magma ocean probably set important parameters for what happened next, things like plate tectonics or the atmosphere. And those early conditions, of course, were the conditions which favored, obviously, the formation of life and the survival of life on the planet. And so in some intrinsic sense, understanding lava worlds is understanding, where we came from and perhaps the destiny of planets as they form and then evolve through time, either to become like the Earth, and Earth-like and very clement for life, or planets like Venus, where conditions are extremely different than the Earth, and where life, basically as we know it, can't exist. So Earth is presently not in this state because of energetics. Where are the sources of this energy for melting rocks in rocky planets? Well, there is the present heat source of the Earth, which are long-lived radioisotopes like those of uranium. Those last for gigayears. It's relatively slow, and so the energy released is not that much. There's, of course, on the other side, the energy released during the initial formation, which is enormous, but short-lived. That's just the energy from gravity. Then there's the irradiation from the star, or the sun, which is actually pretty modest at the Earth's level, but as I mentioned before, can be much higher for planets that are much closer to the star. And there are tides. If a planet has a satellite, or it itself is on a non-circular orbit, it can be stretched and squeezed by the star or by other planets, and that tidal flexing is dissipated in heat, which can be significant. There are more exotic sources like electromagnetic induction, just like a generator is a magnet basically that produces a field, and then wires that pass through that magnetic field in motion produce current. That a planet which is partially conducting, passing through the magnetic field of the star, if everything is hot, is sufficiently intense, the magnetic field, can produce currents in the planet, which their dissipation produces internal heat. And then also analogous to the early formation, in the early solar system, and we suspect most planetary systems, there were short-lived radioisotopes. These are different isotopes than those like uranium, and these decay quickly. That's why they're short-lived. And the ferocity of that decay and the abundance of these isotopes means that a lot of heat is produced or yielded, enough to actually melt rocks several times over, we think. So in this review article, you'll find a little cartoon sketch based on some basic calculations of, in time and space, which energy source is dominant here. And so long time scales are at the top, and then far from the star is to the right. That's where we are presently. And so the dominant heat source is actually long-lived radioactivity, which I said is basically not sufficient to melt silicate mantles. But if you go back in time or closer to the star, you will find yourself with very different energy sources that can be enough to basically melt the planet. So the Earth is not a magma ocean planet are any of the other rocky planets in our bodies in our solar system, magma ocean planets or lava worlds? Probably not. Even the planets that are closest to the star, Venus, to our sun, Venus and Mercury, have surface temperatures which are far below the melting temperature of silicate rocks, which is at sort of minimum at about 1100 Celsius. In the interior of Venus, it is speculated there might be deep down a magma ocean, very deep, but since that's not close to the surface, we don't consider that a lava world. There is another object called Io, which is a satellite of Jupiter, and because of perturbations between the satellites, it's not on a completely circular orbit, and it's orbiting within the strong gravitational field of Jupiter. As a result, it's experiencing tides, extreme tides. That flexing is actually sufficient to melt parts of the mantle of Io. And perhaps there might be some sort of magma ocean within. It has been proposed. We're not sure about that. But future missions like JWST and the Europa Clipper might give us enough information to answer that question. So to definitively find a lava world, you need to go back in time, or that's one option, right? To go back, for example, to the early solar system when accretion was very energetic. And this accretion, again, is basically smaller bodies forming larger rocky bodies like the Earth. For those who like the math, you basically have a term which is the energy per unit mass, which is related to the strength of the gravitational field of each of the objects. And then on the right-hand side is basically how much mass is coming in onto that growing body versus time. And it's sufficient to basically melt, at least at the late stages, when the bodies are big enough, to melt rock. And so the big example of this, of course, is a last impact, the giant impact that formed our moon, and that was thought to actually have melted substantial portions of both the Earth and then obviously the body that hit the Earth and contributed material then to what would become the moon. In fact, the earliest evidence, substantial evidence for a magma ocean on a body is from the moon, because the moon's highlands, the light stuff that you would see as you're watching for the eclipse, that's dominated by rocks called anorthosite, which are relatively low density. So that density is partly responsible for the highlands being high, but more profoundly, it's indicating a strong chemical fractionation of the material that went into the moon, with buoyant minerals floating to the surface. In order to float to the surface, you need something to float in, and that floating would be a magma ocean. So an anorthosite crust crystallized on the moon shortly after its formation, and that happened from, as far as we know, from a magma ocean. That's consistent with all the data. So that's the solar system, at least early in time. If you want to now use the power of exoplanet research to study lava worlds, we can profit from looking at objects that are closer to the star. So you go to the left in this diagram, because as I showed you in that scatter plot, most of the planets we actually know about at other stars orbit well within the orbit of the Earth and actually well within the orbit of Mercury. So they are hot and they can have temperatures which are actually just from the radiation of the host star approach the melting point of silicates. So here's again this diagram, and you'll notice that if you go to the extreme left, there are objects down there, those rocky planets. We know some of them are truly rocky, some of them are just guessing, are actually orbiting in orbits that are less than 1 Earth day. So every 24 hours they go around their star. So you can imagine how close that is. And of course, the inverse of that plot is to use a kind of metric of how hot the planet is. We call it the equilibrium temperature, just making some simple physics that relates temperature to the distance from the star and how bright the star is. And so you can plot those innermost closest planets with equilibrium temperature Radius is again the vertical axis. So the rocky planets, the size of about the Earth, are at the lower part of this diagram. And I plotted here basically the solidus of peridotite here, which is basically a shorthand term for the upper mantle composition of the Earth. And so you can see objects that are well within that, or hotter than that temperature here. So we don't know exactly what those temperatures are because this is based on a simple physical relationship, but they're probably not too different from that. So there almost certainly are objects around other stars that we are detecting now that are lava worlds in the sense that they have substantial amounts of silicate melt on their surface. So I'd like to spend just a few minutes talking about sort of the complexity of lava worlds, because this, I think, is very important in trying to understand not only sort of what is going on for these few objects, but perhaps how to interpret the evolution of planetary systems in their constituent planets more broadly. So again, you could start out with a magma ocean, okay, that occupies the entire planet, to say, and underneath that is a silicate mantle. So in this cartoon, the magma ocean's on top, and then the solid silicate mantle is beneath it, and depth into the planet is going downwards vertically. And of course, there will be crystals that form from this, and unlike water ice, most bulk materials that form planets are basically, their solids are denser than the liquid phase, and so that will settle, okay? Except at higher pressures, at sufficiently higher pressures, that is actually not true. And sort of like ice, then the solid form actually can be less dense than the liquid form. So those crystals will float, at least up to the point where they become a pressure, where the pressure is such that they become denser again, and then they stop. So you could have complex structures in these magma oceans where you have an upper magma ocean and a lower magma ocean partitioned by a sort of intermediate zone where of a slush, where crystals are settling and hanging out. That's, again, due to the fact that at extreme pressures that you'd find in the interiors of some of these bodies, there is a crossover point where liquid phases and solid phases reach the same density, and at higher pressures, then the density switches. And so that's a function, of course, of the material. But overall, higher pressures promote the crystals to be less buoyant, more buoyant with respect to the melt. And a bigger planet will have a stronger gravity, and of course will be deeper in terms of radius. And so overall, you would see this phenomenon appear on the more massive planets. And unlike water, which is one molecular substance, H2O, rocks are made of many elements. They can form a variety of crystals from a melt. And as the crystallization proceeds in a magma ocean, and it cools or forms after some, say, accretion event, the elements will partition or move into the solid phase preferentially at different amounts. And that means that the chemical composition of the crystals will not be the same as the melt, and as crystallization proceeds, the chemical composition of the melt will change. So over time, the magma ocean's chemistry will change. That means that all the other properties of the magma ocean, including its melting point, as well as density, will change as well. And one of the things that I'm exploring here with my colleague Clint is the idea that perhaps we can predict the behavior of planets based on sort of simple initial conditions, where one of them is basically an element, the abundance of an element that is strongly affecting the density. It's a heavy element. It's iron. It's one of the heaviest common elements in planetary mantles. And the other one is simply this pressure term that I mentioned, which corresponds to depth and also the gravity of the planet, which again is related to its mass. So on one axis you have iron content of your mantle, and on the other you have basically the size of the planet. And different planets will appear at different points in this diagram, and then their magma oceans will evolve perhaps very profoundly differently depending on where they start off from. And I've been talking about silicates, that is, combinations where silicon and oxygen are the dominant players. There are hints that perhaps the chemistry could get a lot weirder around exoplanets, and one of those hints is the planet Mercury, where we see what might be elemental carbon in the form of graphite at the surface in large amounts. And it is proposed that due to the sort of strange chemistry of Mercury relative to the other planets, where oxygen is reduced, it's basically less abundant, carbon may play an important role. And in a magma ocean, carbon would separate out as, not as a crystal, but basically as an amorphous substance. Actually, at high pressure, it does form a crystal. Anybody know what crystal that is? Diamonds, yeah. So, on Mercury, the pressures are not so high. Carbon is mostly in graphite. Graphite is low density. It floats to the top. So Mercury may have had not a silicate crust, but a graphite crust. And then maybe deep in its interior, there might be some diamonds. So that's the sort of big picture for magma ocean worlds or lava planets. We now have the ability to actually make measurements of what is happening on these things thanks to some of the new observatories that have appeared on the scene. And I'm just going to highlight the James Webb Space Telescope, which was launched back actually about the time that we wrote the review paper, because it's basically a lava worlds explorer from my point of view. Unlike many telescopes like the Hubble, which basically mostly looked at the wavelengths of light that we see, the James Webb Space Telescope, JWST, can look at much longer wavelengths in the infrared, where lava planets, because of their high temperature, will be glowing. And so basically, it can say something about these planets based on the light that's coming from them, and something beyond the mass and radius that we get from other techniques. So one thing is that the hotter an object is, the more it glows, and the shorter wavelength at which the radiation appears from that object. And so I mentioned the primary transit, which is the when the planet passes in front of the star. So what happens when the planet passes behind the star? It has to happen, except on very eccentric orbits, every time. So there you have the opportunity to make an observation, or two observations, one where the planet is behind the star, and the other one where it is not, sort of a peekaboo. And if you take very precise measurements of those two scenarios and difference them, that difference, that measurement, is the emission from the planet, assuming the star hasn't changed. That's another issue. So you can make, in the infrared, a measurement of the light being emitted from a rocky planet close into a star, hundreds of light years away. At least the JWST can do this. And then there's this simple relation you can write down, for those who like equations, that basically relates how much energy the planet is absorbing from the star, and then how much of that is basically re-radiated back to space. And those have to balance overall over the planet. And on the second term, that gives you the temperature of the planet, because it's basically irradiating something like a black body. And it gets even cooler than that, because if you think about it carefully, look at the cartoon, what you're seeing is just the planet facing you as it disappears behind the star. And that is also the face facing the sun, or the star, the central star. So if a planet is not rotating, if it's, say, locked to the star by tides, and it doesn't have an atmosphere, then you're seeing basically the rock that is directly facing the star and is losing heat only by radiation. But if the planet had an atmosphere, then that planet would have the ability to circulate heat around through that atmosphere to the far side of the planet, which you don't see, but which is radiating to space as well. That's effectively acting to cool the side of the planet that you're looking at. and therefore the temperature should be lower. That appears as the far right term as the D in this equation. But basically, you can say that if you know something about how much energy the planet's absorbing, and you measure how much is coming back at you, you can take the difference of those and say, aha, the rest must be going out the backside. And that tells you whether or not there's an atmosphere there. And in fact, a lot of JWST time on that telescope is now being used to make such measurements to basically see whether there's planets around, atmospheres around some of these planets. I'll skip this, but basically you have to know something about the surface albedo, then you measure the effective temperature of the planet, and that can put a constraint via models on how thick that atmosphere would have to be. But what would an atmosphere like that be formed of? A measurement like that of just the radiation coming out alone will not tell you that. You need more information. So we can start to think about, though, what the possibilities are. So on an Earth-like planet, like ours, the bulk solid Earth is generally made of those elements which can easily condense out even at fairly high temperature. So they're not in the gas phase, they're either in the solid phase or exceptionally they would be in the liquid phase. So those have high condensation temperatures, above a few hundred degrees. And depending on their other chemical properties, those would go into the mantle of the Earth or into the core. But there are, of course, elements where that's not true, where their condensation temperatures are very low, much lower, in fact, than the average temperature of the Earth, and so they cannot condense. So on the left hand, so this plot is basically showing the condensation temperatures. It's a little bit more complicated than this because it depends on what molecules these elements are forming. But overall, you would see that on the left hand of the plot are elements like hydrogen, carbon, nitrogen, oxygen. And surprise, surprise, those are the elements that are appearing in our atmosphere as water, as dinitrogen, as CO2, and would appear presumably, and we know actually in some cases, in other planets around other stars with similar temperatures. But imagine that you're looking at a planet to the far right of this diagram where the temperatures are greater than 1500. In that case, then elements which are normally in the bulk silicate mantle, in the solid part of a planet, could appear in the atmosphere. So there are simple calculations. They're not quite so simple because you have to go and make some measurements that tell you some important constants that actually describe this process. So you could have atmospheres where at temperatures above 2000 Kelvin, where instead of nitrogen, carbon, you start to have sodium or atomic oxygen or silicon monoxide as the dominant constituents of your atmosphere. At that point, the planet's so hot also that the light elements have probably escaped the space and been lost. So you might expect an atmosphere, what we call of rock vapor. So we can look for these. These have absorption lines that we can look for in spectra. The catch is that if you look here at the pressures, these are in Pascal, in 10 to the 5 or 100,000 pascals, 1 atmosphere, these are very low, so these are thin atmospheres. So to do these detections, we need planets with very large cross-sections for their atmospheres in order for us to get enough signal. They have to have big, thick atmospheres, right? So there's a scale height that characterizes that, and the hotter the planet, the bigger the scale height. That's great. But then we also want small planets, which have weak gravity, so the atmospheres are big. They're puffed up. So that would work, except the problem is that small planets are very hard to detect. Remember I said that the transit method depends on the size of the planet. And tiny planets are really hard to detect. So what do? Well, we rely on nature's generosity in providing us examples that we hadn't really thought about before we actually discover them. So these are evaporating planets. They are so small that the atmosphere is boiling off to space. They are so hot that that atmosphere is expected to be composed of silicate vapor, vaporized rock. And the only reason we know they're there, because they're so small, smaller than Mercury, is because that rock vapor is accompanied by dust, either being lifted from the surface or formed in the rock vapor wind. And that dust cloud is transiting the star like the planet before it gets blown away into space, forming a kind of tail like you see on the left-hand side of this diagram. But that dust cloud, even though it doesn't have a lot of mass, each of those dust grains, you can make a lot of dust grains out of a modest amount of mass. And the r cubed versus r squared works to make a huge cross-sectional area, as if it was a big planet. And so that we can see. And in fact, this plot here is what we call the light curve of one of these objects. Each dip corresponds to that dust cloud passing in front of the star at a period which is about a day. This planet is very close to its star. And we can now, thanks to a number of discoveries of these objects, interrogate these not just to look at the dust, which doesn't tell us that much, but to look at the gas, which must surely accompany us, so the original rock vapor. Now, the problem before has been basically all the examples that we've known of have been very faint stars. And taking a spectrum of a star over an hour, which is the time it takes to pass in front of that star, and try to spread the light out sufficiently is very challenging, even for the biggest telescopes. And so what has happened now is we found at least one of these, which is 100 times brighter than the others. So that means 100 times more photons. And now we're in business. And so I just spent yesterday testing the patience of my hosts by corralling myself in my office all day, or that was in your former office too, I guess. My office, it is nighttime on Hawaii at the same time as daytime here, operating this 8-meter telescope to get spectra of one of these transits. So I can't tell you any results yet. This is really fresh material, but maybe in a year, if I can come back, I'll tell you what we found. And we want to do more, because from the ground, we only see those wavelengths of light that pass down through us. And if we can go back to space and do observations like that with like the Hubble Space Telescope, which can see in the ultraviolet, there, if you look at the right-hand plot, you will see that that part of the spectrum is rich in the lines of a lot of the elements that we would expect to see, like iron or magnesium. And so our plan is basically to use Hubble to maybe have a first look at the rock vapor atmosphere of one of these lava worlds, which may tell us a lot about what it's formed from and also how it has evolved over time. So with that, I will finish. There's so much to explore for these objects, which are complicated and probably more diverse than our imagination. This is a cartoon from that review diagram that basically, for review paper, that basically shows some of the things we thought of, but I'm sure nature will ultimately show our imaginations to be sorely lacking. That is the pleasure of finding these things out. Thank you very much, and happy to take questions.
Great, thank you, Eric. We can take a few questions now. Does anybody have any questions they had as a result? I have one. When you showed me yesterday when you were making those observations, and you mentioned that that dust cloud behind these evaporating planets represents a loss of mass of the planet. And so I was wondering during your talk if the solar system might have ever had a planet like that.
Yes. So what happens, Clint was mentioning, this mass loss, although it's not enormous, over billions of years, it can actually be substantial according to our models. And not only that, that mass loss, of course, reduces the mass of the already small planet, which makes its gravity weaker, which allows more mass to be lost to space. Weaker gravity basically is more permissive, which accelerates. This is a positive feedback, and is predicted to end in catastrophic evaporation of the planet. It will basically shrink to nothing over maybe a few million years. Something like a comet does when it gets too close to the sun. And so yes, conceivably, if we started out with a planet that was much smaller than Mercury on one of these close-in orbits, and it has to be close, right? You must have the temperature sufficient, say above 2,000 Kelvin, to get you that substantial rock vapor atmosphere, then we would not know. It would have disappeared long ago, or could have disappeared.
And would that dust leave any trace somewhere else in the solar system, on other planets, or in the asteroid belt or something?
Yeah, I think that by the time, so early on, dust could get incorporated into the rest of the material-forming planets, but by the time these planets probably evaporated, which would take maybe hundreds of millions of years at least, then dust would just basically blow into space. It would be lost. So perhaps not. But it is announced, the planet also has to start sufficiently small, right? So if you put the Earth at 1 day, at least according to the models, it would not evaporate. And I have to say that, you know, when I say this, I always add according to the models. We actually, you know, it's very difficult to test these things, except by actually observing what is going on. So we have predictions of how much mass is lost. We can, for example, for a given situation we observe now, and we see the dust, but how much mass is in the gas? Is it the same as the dust? Is it 10 times more? And so that measurement is going to allow us to sum up the gas plus the dust, which is everything, presumably, and test these actual models to make sure they're actually valid.
Great, thank you. Are there other questions in the audience? Yeah? Good, Christine.
I have only one question. And well, first, thank you for explaining the studies of the exoplanets and how you can find out where this lava flows, maybe forming Earths and planets. I wonder if there is this a science? What is the name? Is it many people working on this?
So I think, so for the general exoplanet field, we just call it exoplanet research. I don't think, we don't have a more sophisticated name of that. For these objects, we don't have a specialty except, and they're also called disintegrating planets too. I'm not sure I answered your question, but.
Well, would you consider yourself an astronomer or a planetary scientist or a...
Depends on the time of day.
Yeah, okay. So
and the day, right?
Yeah.
So, I mean, traditionally planetary science has been confined to the solar system, and astronomy has astronomy is the birth of exoplanet research. It's the field in which it grew up. And that's because they were detected by astronomers who were actually working on stars. They weren't actually working on planets at all. They were working on stars, and they were using sort of classical but refined techniques that astronomers use. So they were doing astronomy, and they're astronomers. They got the Nobel Prize for it, so not too bad. And for the longest time, all we could measure was, for example, what was the mass of a planet, and maybe how big it was, but mostly just the mass. And so like you can imagine, is what we call point mass, sort of idealized mass going around a star. So that's astronomy. You know, binary stars are like that. It wasn't until we actually could make other observations, like the size of the planet through this transit technique, and then also the temperature, and now we are studying their atmospheres, that they become more, excuse the pun, solid. They become more real. And they have processes on them, and they have history. They're not just a point mass. We don't live on a point mass. The Earth today is very different from what it was before. It's clearly very complex. And so now astronomy is, although it was the original home, exoplanet research has now started to wander and expand into those other fields, which is quite exciting, I think.
Yeah, and that's something that Fab is very interested in. Any other questions in the audience? Trond?
Yeah, maybe a simple question. You know, I guess all the terrestrial planets were once lava worlds for a little time. And if we get a moon forming, if I ask someone working with magma ocean on Earth, I ask them, so how long did it last? And they typically give me a million or a few, very fast, okay? So my question is then, if you go then closer to the sun with Venus and Mercury, is that close enough that it lasted longer, the lava world there, compared to Earth?
Yeah, so the question is basically how long can these magma oceans last? On the Earth, it's true that the interval was probably very short after the moon forming impact. What it crucially depends actually, or one factor crucially depends is whether or not these oceans are insulated from the surface, either by an atmosphere, but especially by something that can only conduct, and that is a solid layer. So a planet on which the magma ocean is at the surface, that heat is easily lost by convection, overturning in the ocean, and then radiation to space. But, and that's the case if for example, solids are denser and they settle all the time. However, on a planet where the composition is different and where solids can rise to the surface, like Mercury maybe, even though it's graphite, that can serve as a conducting layer. And conduction is a poor means of transporting heat. So it takes a long time to cool. So a short answer is yes, on Mercury it could, all else being equal, it could be longer. But Mercury is a very much smaller planet, and it didn't maybe have a moon-forming impact. So it's not clear. But basically, this will tell us, whether or not a magma ocean on this planet, the relative density and the position with respect to crossover will tell us probably a lot about the lifetime. And that sort of folds into this diagram that I have showing just in cartoon form, where how long a magma ocean can persist and where is going to probably depend a lot on the composition as well as the size of the planet. And that actually gives rise to the speculation of Venus, if you make some certain assumptions, that it could still have a magma ocean at the bottom of its mantle, because that's where it settled because of density considerations, and it's very hard to get rid of all that heat very quickly.
Okay, maybe one last question from Reidar.
But it's no, this is just a comment. I mean, you mentioned Venus having possibly some relatively deep or shallow magma ocean, but so I'm not sure about that. But what is seemingly relatively clear from the last seismic studies of Mars by the InSight mission is that Mars seems to have a basal magma ocean of about 150 kilometers deep at the core mantle boundary.
Yeah.
Above the core mantle boundary. So,
Yes.
so yeah, I mean, a hidden and buried deep magma ocean can last. And the Earth, I think that the Earth's magma ocean, basal magma ocean, lasted probably throughout most of the Proterozoic.
Well, and then there is still speculation there may be a fluid layer at the base of the Earth's mantle, which may be some residue. We don't know. Yeah. Yes.
Okay, maybe that's a good... Oh, one more question from Stephanie.
From the boss.
So you have introduced now lava planets, where we can understand from the atmosphere the composition of the planet, and we know some of the planets in the solar system are linked between atmosphere and interior. But how do we deal with all these which are like Earth, where the composition of the atmosphere is completely different to the interior, to interpret our diagrams which you have shown, like mass and radius?
Yeah, so that's a very good question. So how do we relate, basically, how do we back out something about the interior of the planet from what we can observe with the telescopes in the atmosphere? And that's the 50 million kroner question, which is going to involve complex models of how these observe. And what I will say is extremely important for those models, because some of the physics is actually simple, is the chemistry that's required for melting and also for vaporization. So a lot of geology is based on not ab initio first principles calculations, but just going and measuring something. You know, at what temperature does this rock melt? So we have lots of data for the Earth in Earth-like compositions. And what I'll make a pitch for, to anybody who wants to listen, is what's really needed is more data for non-Earth-like compositions, because it's sorely lacking. And if you take the models that we have based on Earth-like compositions and then try to run them a little bit outside the box, outside the comfort zone, they break. I know this from firsthand experience. And that's a field that is wide open and infinite in depth and complexity and wonder. Great questions, thank you.
Okay, on that note, we'll close, and let's thank our speaker once again.
Thanks to people online.